So we are discussing about this particular Bayes rule for computing these conditional probabilities and the relationships between the conditional probabilities of two events. As you can see in this rule, if I consider there are two events A and B, and of course you have to consider that at least when you are expressing in this form, the probability of A should be greater than 0. Then this expression is true. Then the conditional probability of B given A is given by this expression. That means you are considering the joint probability of A and B, and then you can divide by probability of A, or even joint probability of A and B can be expressed as in the numerator, as you have seen, that probability of A given B.
Hello.
Is there anyone who is asking any question, or someone's microphone is just on? I think please mute your microphone in that case if you are not asking question. So this example, what I mentioned in the previous class, I think we worked on that particular example. There, we considered this rain and the other event like the grass is wet, and the table, what it shows the conditional probability of that the grass is wet given rain or not rain. So there are two possibilities when the grass is wet: either there is a rain or it does not rain. And for each possibilities, for each event, the conditional probabilities are given when the grass is wet and when also the grass is not wet. And we can see that we can compute given this information, this table, and also the probability of rain. That is another piece of information on top of the table. You can see that it is given as 0.8. So given this information, you can compute probability of rain given the grass is wet. That means you can ask the reverse question that if you observe the grass is wet, then what was the probability? What is the probability of rain? That means it's a rainy day. So we worked out on this particular example in the previous class. So let me proceed from that point. In the Bayes rule, as you can see that these conditional probabilities of one event given the other event is given. So in this case, as if though it does not always mean the causality, but still this arrow denotes some kind of it's an indication of causal relationships. It's not exactly always it has to be causal. So this information that when you are expressing the probability of W given R, then you have the arrow from rain to W. So that's the kind of notation, graphical notation of expressing Bayesian conditional probabilities. So we'll come to these kind of notations later on also. So this is a kind of information that is available. Now, the other way that that we call inference. That means if I find the probability, if I find that the grass is wet, then what is the probability that it has caused due to rain? So it's a kind of question many a time we'll be considering. So for example, when we are trying to classify, we may ask these questions that we have the observation of an instance, and then given the instance, what is the probability of class? Or because you know that sometimes it is easier to get the other information easily. For example, given a class, you can observe what is the distribution, what is the probability distribution of different instances within that class. Now, if I ask you the question that given an instance, what is the probability that it belongs to class? So then it becomes an inference, and that is what is the classification. We'll come to those kind of inference also subsequently. So in the context, as I was explaining, that we consider that the instances are evidence in this case. That means our training examples, the instances, they are evidence, and there is an hypothesis which is which is responsible for the particular evidences. That is evidence with examples and levels, something like that is the evidence. And so if I provide you the probability of evidence given a hypothesis, so you can start with an hypothesis and you can find out that what could be the probability of that evidence which is adhering to this hypothesis, which may be due to this hypothesis, which may occur due to this hypothesis. And then your objective is to find out finally that what is the hypothesis, what is the probability of hypothesis rather given these instances. And if you apply the Bayes rule, you can compute it in this form that if these probabilities are given to you, we assume that probability of E given H is given to you. That means it is easier to compute that part. And then also there is certain kind of probability of each hypothesis within the hypothesis space. And we call it prior probability of a hypothesis. And also we can have the total probability distribution within that instance space itself. That we call marginal probability. So this is called prior, this part, and this is called likelihood. That what is the likelihood of occurrence of that event given the hypothesis. So these are the technical terms which are often used, and sometimes we'll be using this term instead of telling you in terms of probabilistic statements. So, but they are all probabilities. As you see that if I use the term prior means it's a probability of certain element which is already prior terms. It's a kind of the prior terms comes from the fact that it is something given, it is something that knowledge is already available in some form. So prior probability tries to capture the domain knowledge in that sense. And the likelihood is also it is a kind of class distribution. So given that class or within the class, what is the distribution of the instances? Or given the hypothesis, what is the probability distribution of different evidences? And then the this is actually called posterior. So you are computing the posterior probability. So which is the given the evidence, what is the probability of hypothesis? So these are a bit technical, and whenever we use this term, we have to always interpret with respect to these probabilistic definitions. Now, the Bayes rule, I have worked out the example in the previous class also. You can see that that's a special case when we consider a very generic situation that you consider all different possibilities of outcome of an event, say event B. I should say these are all outcomes, so B1, B2 to Bk. So these are the outcomes of different event of an event, and what is the probability that a particular and also these are all mutually exclusive outcomes from naturally. I mean, these are the outcomes on the sample space, and you are considering the probability of a particular event Vi given A. Now this can be written as probability of A given Vi into probability of Vi by probability of A. In the denominator is probability of A, and which we can express in this form. So this A can occur with any one of these particular events. So B1 to Bk, they can jointly occur. So if that is the kind of situation, suppose the example was that grass could be wet, either there is a rain or there is no rain. Still, a grass could be wet. Only there are two possible events which will happen with the occurrence of grass. So then you can consider joint probability of each one independently and each one separately rather. And if you sum this probability, that would give you the probability of A itself. So that is what you should note here, and we use this particular particular computation. So I'm not able to use the pen here. Today I'm not able to use the pen, so it's difficult. I do not know. I have to check later on. Anyway, I hope you have, as I was indicating, that the denominator part, when you are expanding that probability of A, it can be expressed as sum of all joint occurrences of A with all different mutually exclusive outcomes of a particular sample space of that particular type of events. So this can be also written in this form. So let us come to this this particular concept once again. Now, I have so far I have discussed about about the events and their probabilities, and let us consider the uh, the event as an outcome of a random variable x. So it's a numerical outcome of a random variable x, and then what is the distribution of that outcome? So so that is what we consider a distribution of a random variable. That is the collection of possible outcomes along with their probabilities, and there could be so if your random variable is discrete, then it is a point probability distribution that we would be considering. So at every possible discrete value of that random variable, you consider what is the probability. So here you can see that we have given this theta, which is actually which is a parameter. I think what I should do, I should close all my no. So let me. But it will be too slow now. I understand what is the problem. Problem would be this hypothesis evaluation. There is something more being displayed. It takes time. Sorry, there is some technical hiccup at my side, so let me continue with this. So then if you consider the continuous case of a random variable, then you can see that the random variable can be considered. So when we are trying to compute the denote the probability, it is not a particular point observation because it's a continuous variable. So we can consider that what is the value of x within an interval. So what is the probability that x will lie within an interval? It is not value of x. What is the probability that x will lie within an interval? And we assume, of course, x is having the real values in this case. So here also, as I understand, you can consider that this random variable it is having a single dimensional space.
Yeah. Is the probability distribution function here, sir?
Yeah, it's a probability distribution function. That's right. So you can see that there is a concept called probability density function. See, this p theta x is a density function because when you are computing probability of an interval, so you are integrating that density over that interval. So that's why the term is probability density function. And when you are integrating, as it is explained there itself. So these are the two ways this probability distribution of a random variable is denoted. One, as if the probability values of at each possible discrete values when it's a discrete case. So it's a probability point function. And the other one is a probability density function. It gives a probability density function, which means probability at a point x, it gives you the density. So if you consider a small interval around x, and if you integrate, then you will find out actual probability that what should be the what is the value of actual probability of x being within that interval. So any interval you consider, and if you take the corresponding integrations of the density function, you will get the actual probability. So that's what I was mentioning, that you have probability density function. The other one is called probability mass function. So some examples of random variable. Suppose you consider the sample space, that say set of all sequences of 3 rolls of a die. And now, for each sample space, I mean for each kind of outcome, you consider x is a random variable, which is the sum of the number of dots on the 3 rolls. That means it's basically the dice. So 3 die. So what is the sum of the outcomes of 3 throws of a die? Okay. So that sum itself is a random variable. So how many possible values it can have? If you roll 3 thrice a die, and if you consider the sum of all the outcomes after 3 rolls, so
18.
Maximum would be 18, okay, and minimum would be
3.
minimum would be. So you can see that the
Would be
value,
3.
yeah, minimum would be 3. Is it okay? So
Yes, sir.
So the values will lie between 3 to 18, and naturally, if I say what is the probability that the sum is 1, the answer should be 0, right? Or what is the probability sum is 19, the answer should be 0. But it has certain probabilities for each values within 3 to 18. That is what is the probability mass function. So you have to compute them. Say what is the probability of x equal to 5? So how do you do it in that case? Today, I'll not be able to write anything. I have to check the technical issues. So you have to do it and you have to tell me. So take the first one itself. What are the possibilities? X equal to 5. So what are the possibilities? Can you enumerate? Because you have to enumerate, right? So you can fix the first two and let the third one be the free. Huh? So you can have, say, 1 1, then 1 2, right? Then 1 3.
3 possibilities.
3 possibilities only. No, see, it can repeat. No. Why 3? Because 1 1. See, I'm just saying the first two. I'm not arguing the third one. Third one is implied. Third one would be implied. So as you can see that in any outcome, the maximum value of a die could be 3. It should not be more than 3 to give it 5. I'm answering the question of 5. Huh? Okay. So it is 1 1, 1 2, 1 3. Similarly, right? The other one also 3 into 2, that is already 6. And then there could be 2 2, that is 7, I think. Is there any other thing? No, sorry. The 1 1 is also symmetric. So there is 6, I think. You're right. Okay. So 6 outcomes. But what is the probability?
6 by 6 into 6 into 6.
That's right. So which means 1 by 36. Okay. So this is the probability of x equal 5. Please check. I mean, I'm just telling offhand. So you have to also check that whether there is any mistake in my part, on your part also. So let me now go through some of the other definitions with respect to random variable, and often we will be using these definitions and their meaning. See, if I consider a random variable x and whose probability distribution is given in this form. So distribution, when I say distribution could be interpreted if you consider the variable is discrete or variable is continuous as per his own context. So in this case, of course, we consider it's discrete because you can see we have used the summation term while defining expectation. So actually, what is expectation of x? What it is giving you? So when we say in terms of our common notion that expectation means if you go on experimenting, what is the most likely value that you are going to get, something like that. Or rather, I should say, that's not always true. I mean, what is the average? What is the average over the corresponding average value over the whole experimentation? Average time, on the average, what is the value you will be getting? Or you can say also, it is almost similar, but that is what is expectation. On the average, you will try to get this value. It is also can be considered something like which is most likely. Also, you can say in other common, in a loose way, you can say that also. But no, the mathematical definition is very tight. It is, as you can see, it is simply the weighted average of the values of random variable where weights are given by the probability of that particular weights, right? So do you agree? Is the weighted average? Weighted average of the values in the random variable. So expectation of a particular distribution, when you say distribution, because as you can see that it is tied up with the not only with the variable but also with the probability distribution. So expectation of a random variable given certain probability distribution is defined in this way. There is another term. In an empirical sample, we can have an estimate of an expectation like this. So it's an estimate actually. If you are considering, this is just the common average. You are assuming all are equally probable. You are assuming all are equally probable with that. So this expression is with respect to equally probable events. Then in the continuous case, expectation is defined in this fashion, in this context. So you can see once again that almost similar it is. So you have the integrations and you are doing integrations over the whole space of the random variable. And then you can also define expectation of sum of random variables. In fact, it can be shown that it's a linear operation. So if you have a sum of random variables, then expectations will be also sum of expectation of each component. So expectation operation is a linear operator because the summation and integrations, these are all linear operators. There is another concept over the for the distribution, another parameter or property of distribution that is often used, that is called variance. And you know that the variance in this case, it is the expectation of the sum of square of the deviations, I should say, expectation of square of the deviations of the random variable from its expected value. So it's a common, if you just extend this notation, if you see the analogy with respect to the standard definitions of variance of given a set of sample values, it is simply, it corresponds to that. And similarly, there also we are very familiar with this kind of reduction, that this definition can be finally reduced to compute variance. Just you find out the difference between expectation of its square minus the square of expectation. So this is how the variance could be computed. So given this, let us consider also some of the kind of experiments and the kind of distributions they follow. And given those distributions, you can consider that what is the expectation and what is the variance of that distribution. So here, one of the distribution which is known as Bernoulli distribution, and this distribution is applicable when you consider an experiment with binary outcomes. That means either 1 or 0. You can say toss. Toss is an experiment, tossing of a coin, single toss. It will have a binary outcome, say head or tail, something like that. Or any other kind of process you can model where there is a binary outcome. That is also you can consider. Suppose I would like to have a classification task, and either it belongs to a class or does not belong to that class. If that is the situation, then that is a kind of binary outcome situations. And this kind of process or experiment, it follows this distribution. That is interesting. So if you can characterize it, and then simply you can apply its theory, this Bernoulli distributions theory. So what is this theory? Is pretty simple. Actually, there is only one parameter of this distribution. That means it gives you you need to specify only what is the probability of one of these outcomes. Then naturally the probability of other outcomes are also defined, right? Because it's a binary situation. So you see that there is a parameter P, and this P is interpretation is that in this case it has been shown as probability of x equals 1. So naturally probability of x equals 0 would be 1 minus P. And you can find out very easily that expectation of x equals P. Do you agree? Do you agree that expectation of x should be equal to P?
Yes, sir.
Fine.
Yes, sir.
Good.
Why that expectation of x?
Why? Somebody may answer. Why expectation of x equals P?
Because it's P
Because second is
1
0.
plus
1 and 0 and 0 multiply anything will.
Right. So the values are important, isn't it? So if I take different values, then naturally expectations will be different. If I consider the value of x is it is represented by two different values, then no, you should not consider expectation of x should be equal to P. You should also understand that. Similarly, the variance of x also you can find out. It is P into 1 minus P. Okay, is it clear? So with respect to that, let me tell you one thing, that no, you have used this Gini impurity measure in the decision tree. In fact, there is some definitions that we have used there. Actually, you are measuring for these two-class situations the variances. When you are considering these binary situations, you are measuring their variances. Yeah. Now, you can, in that definition in my class, it was a bit non-conventional definition what I have given. So later on, I found that the conventional definition is slightly different, actually twice of that value. So I have changed expressions and updated that slide set in the module. So you need to check that part, because when we ask to measure something, to compute something, it has to follow some conventional definition, not non-standard definitions. Okay, so earlier it was a non-standard definitions. So please check that with the updated slide. Anyway, so let me then go through another kind of distribution that is called binomial distribution. Now, binomial distribution, it is kind of, you can say, it comes from the from the experiments involving Bernoulli distributions. Only those experiment is carried out n number of times independently. Okay. When you have an experiment which follows Bernoulli distribution, and then if you carry out that experiments n number of times independently, then you consider certain you count how many times it was successful or it was failure. So one of them, either you count how many times it was successful. So it's considered. So that is your variable. That is your random variable now, right? That is your random variable. So how many times it is successful? Now this random variable will follow binomial distribution. So you should, once again, you should be very careful about the context on which these distributions are applied, on which these distributions are considered for a particular type of experiments. So this is what I mean. You have an event experiment following Bernoulli distribution with parameter p, and then now if I consider n number of times, and then you sum them, because the outcome is either 0 and 1. So if you sum them, it is counting number of ones. So if you sum them, then that variable will follow the binomial distribution, and it has now two parameters. P is one parameter, and n, that is number of draws, is another parameter, right? And so, in fact, you can very easily show that using this combinatorics, you can show that this distribution, which is once again a discrete distribution, because how many values it can have, this random variable? It can have n values, okay, 1 to n. And outside that, no, it will not have any value. It can have 0 also, sorry. It can have 0 to n. Okay, do you agree? It can have 0 to n, and outside that, of course, no, it does not have any value. So, there is some mistake in my slide. It should be x equal to 0, 1, 2 to n. Okay. So random variable x stands for right. So this is the thing, and you can compute what is the expectation of x. You can perform these computations. You can do the algebraic manipulation, and you can find out that expectation of x equal to n into p, which is from our common sense, it is also intuitively it is also suggesting that. It means what? What is this expected value of sum? It is basically the p gives you the probability of success. So if you are fraction of time you are expecting, that would be out of n outcomes, you are finding out what is the fraction of time it is on the average it would be successful. That is what you are doing. So n into p, and that is the number of success, right? And then the variance is given in this n into p into 1. You note that this n into p is not an integer, though x takes all the integer values. Expectation of x is not an integer. So expectation of x, it is basically a real value, right? So it is something like you are trying to average over the whole number of. So if you count and then you just divide by n, that's all. That is what you are trying to do. That is of course the expectation of x. So some of the plots of these distributions, if you look at this distribution, you can find out that there is a bias, right? There is a bias. Actually, this expectation is giving that kind of, I should not say the term bias here, but I should say around the value of expectation, the distribution is maximum when at the expected value, and then no, around that value again it gets it gets reduced. It is decreasing, and you can see this kind of. Though it is a discrete distribution, in a continuous way, if you try to plot the envelope, it would look like a Gaussian distribution later on we will see. So in fact, that is the fact that if you increase more number of trials as n tends to infinity, this distribution will be tending to a Gaussian distribution. So there is another distribution which is called Poisson distribution. It is also a kind of special case of binomial distribution. Here we assume also, here also we are assuming that n is tending to infinity, and we fix, but we are fixing the expectation to a particular value lambda. That means as n tends to infinity, as you can understand, if lambda is constant, p is going to be tending to 0 also. But no, the product is that is the interesting part. Product is constant. So p will be basically lambda by n in that sense. And then actually, and binomial distribution becomes Poisson distribution. And this distribution, it looks like this. I mean, this is the functional value. So you can see what is the sum of p theta x. If you consider here, actually theta is lambda, right? The parameter theta is actually lambda here. So it has a single parameter lambda. And if you see lambda to the power x by x factorial, if you sum it from x is equal to 0 to infinity, then what is that value? What is that series?
E to the power lambda.
It is e to the power lambda. So naturally, sum is giving nicely, because that is one of the properties of this probability distributions, particularly when you are saying probability mass function, it is sum, and if you consider probability density function, it has to be integrations over that interval. So they should be equal to 1. That's total sum of probabilities over all the values, that should be equal to 1. So that is also satisfied. And here the expectation of Poisson distribution x is lambda, and whose variance is also found to be lambda. So these are the you need to do it, algebraically. You can compute it, you can do the calculation, and you can show analytically that this is a fact. Use the definition, and very easily you can prove this thing. So that is one interesting fact about Poisson distribution. You can see its expectation and variance, they are the same values for the Poisson distribution. So if you look at the Poisson distribution also, you can see that Poisson distribution also looks like this, and once again, no, it has that nature of normal distributions. So now let me give you the brief introduction of summary of normal distribution. It is super binomial and Poisson distribution, even the Bernoulli distribution. These are all the cases of discrete random variable. Those distributions are related to the discrete random variables. But when you consider a random variable in the continuous domain x, that means it takes any real value from the real axis. Then there is a distribution, and very popular and very well-known distribution, that is called Gaussian distribution. The term normal comes because more often we observe this kind of distributions in our in various phenomena, in various natural phenomena. The property is that it's basically on that there is an expected value around which this distribution is symmetric, and it can take any value from the real axis. So this is the expression of the probability density function of the Gaussian distribution or random distribution, normal distribution. And you see that what are the parameters in this case? There are two parameters in this distribution. One is mu, another one is sigma. And they are all related to the corresponding expectations and variances. So mu is the expectation of this distribution of this for this random variable, and sigma is the sigma square, I should say, is the variance for this distribution. So these are this is two things that you should know. Now suppose I have, say, two random variables x1 and x2, and you can see that you have this mu1 sigma 1 square, that is one distribution. The other distribution is characterized by these two parameters mu2 sigma 2 square. So what do you expect? What should be the distribution of sum of these two random variables? In fact, if they are independent, it can be shown that they are also they are Gaussian. It is not the sum of Gaussian distributions, that you should understand. But the sum of this random variable, they are also Gaussian if they are independent. And in fact, then it is just sum of their expectations. That should be the expectation of the resulting distribution. And the variances also you have to need to just simply sum. That would be the variances of a resulting distribution. So with this, let me conclude this particular topic. It's a very brief review of the concepts of probability, and I understand that most of you are already familiar with this because you have already done this course in the undergraduate classes. And but no, it's just a summary because we'll be using this concept in our subsequent